Something goes wrong. Something goes wrong. This computer, I started this computer. This is how they came here. So somebody has been working there, I think. Okay, do you have a computer? Yeah, attend the meeting. I'm sorry, there's something wrong with the projection system. Open your computer, please. Right? Attend the Zoom meeting. Hi guys, online guys, there's something wrong with the project system in the classroom. So I'm asking these guys in the classroom to turn on their computer to join our Zoom meeting. Just wait for a couple of minutes. Are you guys ready? No. Okay. Here you go. Where are you now? Are you okay now? No. Okay. Just 1 second, guys. I want to make sure all you guys are on the same page. So ANN is a hard research area, and ANN is used for prediction. Okay, so we have ANN. We also have CNN and RNN. And this CNN is not talking about the medium. I'm talking about the CNN. And CNN C is convoluted. The R recurrence. So we have ANN, AI. I'm going to teach you the fundamental, the basic artificial neural network. We have CNN, we have RNN, CNN, and RNN. They are more advanced. Okay, guys? Okay, I see you. You're there also. Jacob, are you there? Yep. Okay, so let's get started. So today we're going to talk about ANN's application in industrial robot. So here are today's objectives. And first, we want to learn the fundamentals of this artificial neural network. What is artificial neural network? And how this artificial neural network works? And what can we use this artificial network for? So we want to learn application of ANN in industrial robots. We want to learn how to use MATLAB and to select and train ANN. And we want to learn how to implement the trained ANN in industrial robots. Okay, so these are the 4 main topics. So what are the neural network? What are neural network? So we have, each of us, we have one brain, right? This is what within one brain we have this neural network. What is neural network? Neural networks are networks, so the networks of neurons. We have billions of neurons in our brain. For example, as found in the brain, so biological, for each of us has billions of neurons, right, within our brain. So artificial neurons, as the name suggests, it is not a biological brain, a biological neurons. They are made by people, artificial. So artificial neurons can are crude approximations of neurons found in the real brain. So this you should know that this approximation, and they may be physical devices or purely mathematical constructs. So mathematical model. Okay, so no matter and how much effort we put to develop artificial neurons, I still believe that our biological neurons are the best in this universe. Right? Otherwise, we will be wrong. Artificial neural networks are networks of artificial neurons and hence constitute crude approximations to parts of real brains, so artificial. So they may be physical device, okay, or simulated on conventional computers. So it can be a mathematical model or can be a physical device. If this is a physical device, actually it is mimicking, this is our biological brains, it's a physical device. from a practical point of view, ANN is just a parallel computational system consisting of many and simple processing elements and connected together in a specific way in order to perform a particular task. So, and from the perspective of engineer, so ANN is just a parallel computational system, right? So, computation. This is mimicking our biological neurons. So one should never lose sight of how crude the approximations are, and how oversimplified our ANNs are compared to real brains. So this is, as I said, our biological neural network are the best in the universe. No matter how much efforts we put and to develop artificial neural network, we cannot outsmart our own brain. Otherwise, and we will be in trouble, right? If you develop something, this guy is smarter than you. That's kind of funny, right? No, way. There's no way. We cannot do that. So, where are artificial neural networks worth studying? So, they are extremely powerful computational devices. They can do the computations, just like how our brains process the data, right? So massive parallelism makes them very, very efficient. And they can learn and generalize from training data, and you can train this neural network, and then use this trained neural network and do something for you, right? So this is mimicking and how the brains work. For example, for a person, if we can imagine a person has never received any education in engineering, in math, right? So how you want this guy to work for you? And first you need to train, right? You need to teach this guy on how to speak English language or other languages, and how to use math to solve problems, right? And in engineer, you need to train this guy and to how to build a model, use abacus, right? And how to develop, how to use the PLC, how to use the IR. You need to train it before this guy can work. So the same thing, training something, training and then ask this guy to work. And they can learn and generalize from training data, so there is no need for enormous feats of programming. And they are particularly fault tolerant, and they are very noise tolerant. So they can cope with situations where normal symbolic systems would have difficulty. In principle, they can do anything a symbolic logical system can do and more. Okay? Now this we have, now I don't know whether you have heard this one or not. For the computation, we have two categories. One is hard computation, one is called solved computation. And solved computation, ANN, is one of the solved computation. Okay? Hard computation means this the linear algebra, this is calculus, this is hard calculation. And for this solved calculation, for solved computing, we have ANN, and we have fuzzy logic, and we have another one is a generic this algorithm. So all these three guys, and they are mimicking how our brain works. And this is called soft computing. So our traditional computing, we call hard computing. So calculus, linear algebra, all these mathematics, and they are called hard computation. Okay, guys? So what are neural networks used for? So the first one is a brain modeling, right? So the biological goal of constructing models of how real brains work, and this can potentially help us understand the nature of perception, actions, learning, and memory, and thought and intelligence, and/or formulate medical solutions to brain damage to patients. So they can do some brain work. So this is a biological framework for people. So artificial system construction, the engineering goal of building efficient systems for real-world applications, and this may make machines more powerful and intelligent, and relieve humans of tedious work tasks and may even improve upon human performance. And both methodologies should be regarded as complementary and not competing, right? Brain modeling, artificial system construction. We often use exactly the same network architectures and methodologies for both. The progress is made when the two approaches are allowed to feed one another. There are fundamental differences, though. For example, the need for biological plausibility in brain modeling and the need for computational efficiency in artificial system construction. For our case, from the perspective of engineer, and we want to use this is INN and to do some prediction for us. Okay? So for example, for the NASA is a Mars mission. You know, I think you guys know the NASA not Mars mission, right? The NASA wants to send something, send a person or people, the crews to the Mars, because Mars is totally a strange environment. And how can we handle this is different situations? How can we do that? We use artificial neural network. When we think about all these is the case scenarios as many as possible, and then use these as the case scenarios. From these case scenarios, we extract the different features, and then we use these features to train the artificial neural network, and then put this artificial neural network in microcontroller or computer, right? And then control and send these instructions to the crews, people. And if they run into this problem, what kind of actions and this guy or guys need to take. So this is use artificial neural network. It's for uncertainty, okay, uncertain environments. So learning process in neural network. So this is learn. If we want to use this is neural network, you must train it. Okay? Otherwise, and this guy cannot work for you. Among the many interesting properties of a neural network is the ability of a neural network to learn from its environment, okay, and to improve its performance through learning. So the improvement in performance takes place over time in accordance with some prescribed measure. So learning. So a neural network learns about its environment and through a iterative process of adjustments applied to its synaptic weights and thresholds. Ideally, the network becomes more knowledgeable about its environment after each iteration of the learning process. So remember two concepts for neural network: weights and threshold. Right? And write down it. So the two most important concepts are weight and the threshold. I'm going to teach you guys. So, and there are three broad types of learning: unsupervised learning, and learning with an external teacher; unsupervised learning, and learning with no help; reinforced learning, and learning with limited feedback. So there were three broad types of learning: supervised, unsupervised, reinforcement learning. Guys, if we ask you guys how many broad types of learning we have learned for ANN, for the neural network, and you should be able to answer this question, right? So this is a brief historical note. So in 1943, so this McCulloch and Pitts proposed McCulloch-Pitts neural model. This is a neural, right? So this is a single neural. So in 1949, the Herb published his work, The Organization of Behavior, and in which the Herbian learning rule was introduced. So Rose-Bland introduced a simple single-layer network called perceptrons. Minsky and Pepper's book, Perceptrons, demonstrated the limitation of single-layer perceptions. And so we have this is adaptive resonance theory and Hopfield, and this Hopfield network, coherent And this is self-organizing feature mapping maps, the back propagation learning, and ART variant networks, and radio basis function, and support vector machines for development. This is the brief history of artificial neural network. And around 2000, a neural network was a very hot research area. But now, and it becomes hot again. Right? So it found that, and this guy, this is artificial neural network. We say AI, artificial intelligence, and they can help us a lot of things when we explore this is uncertain this environment. Right? So this now is become hotter again. So neural network applications, now as we said, brain modeling. So for the patients and who have this damage the brains and the doctors can help them. And the real world applications, I want you guys to know this. Okay, financial modeling. So this is this mathematical modeling, predicting the stock market, and based on you need to train. That means you need to train the neural network. Time series prediction, climate, weather, scenarios, and computer games, right? Intelligent agents, chess, and background. Maybe you have heard the news. The IBM. IBM. This guy is a computer and beat the Japanese chess champion. Do you guys know this news recently? Yeah. Okay. So because this guy, the computer learns very quickly, it can self-learning. When you do it, they just learn from the computer. Robotics. See, this is our job. Autonomous, adaptable robots. Pattern recognition and speech recognition, seismic activity for sonar signals, data analysis, data compression, data training, bioinformatics, is DNA sequencing, alignment. So this is the neural network are very, very useful for us. Okay. For our case, robotics, industrial robots, and how we use the neural network and to do something for our industrial robots. So this is the latest version of this neuron. And so this is neuron, okay? So this neuron, because our brains are artificial neural networks, and they are composed of many individual neurons. So this is simplified model of real neuron. So this is neuron, and we have weights, okay? So this is a connection, and that's I ask you guys to remember two important concepts for neural network. Can somebody tell me what they are? Weight and threshold. Yeah, weight and threshold. So these are weights. Whenever there are two neurons, these two neurons are connected together. So this is a connection. There is a weight. Okay. The threshold is for the neuron. Weight is for the connection between the neurons. And the threshold is for individual neuron. So for this individual neuron, if all this information and this neuron gets is above this threshold, and so this is neuron, it will be working. Otherwise, we will say the information is not strong enough and you cannot stimulate this neuron. Right? A set of synapses, that is connections, these are connections, brings in activations from other neurons. A processing unit sums the inputs, sums together, and then applies a nonlinear activation function. We have a nonlinear activation function. An output line transmits the result to other neurons. These are to other neurons. Right? So this is the oversimplified model. But this model is very version, but it's very good. It's a threshold logic unit. How the model neuron works. So each input, I is multiplied by a weight. Okay? As I said, weight is for the connection between neurons. And these weighted inputs are summed to give the activation level AJ. The activation level is then transformed by an activation function to produce the neuron's output at Yi, and WJI is known as weight from unit I to unit J, the unit neuron I and neuron J. If WJI is greater than 0, this is excitatory. So if WJI is less than 0, is inhibitory. Note that II may be external input or the output of some other neurons. So this input for this neuron might be from internal, external input, or from output of other neurons. Okay, guys? So this is how it works. So here, this is mathematically. So this is your output. This is a sign. This is a function. This is a function. This is theta is the activation threshold. Right? If the sum of all these inputs, weighted inputs, and they are greater than theta, and say this neuron will be stimulated. Otherwise, this neuron will stay there, will not do anything. The threshold. And the stress, this we call threshold here, but the same thing called in MATLAB is bias. Can we write down it? Bias. I don't know why should the MATLAB use this word, bias, B-I-A-S. They use bias and to stand for the threshold. Okay, here is the statement. So this neuron is an extremely simplified model of real biological neurons. Nevertheless, they are computationally very powerful, and we will use this one. Right? They are very, very useful. So I have talked about this as how the history of neural network and how it works, and now we are going to talk about and why we want to use this application of this is ANN in our industrial works. Right? So industrial works, we know that robot can efficient, adaptable, safe. And however, this robot can do a lot of good things, right? This let me show you guys. So you can program this industrial robot and to do the welding work for you. Welding, you know, have you guys ever done the welding work? No, right? Okay, so welding work, I don't like it because I don't have a very good eyesight. I need to use that cover to protect my eyes, right? So this glowing the light. So also very easy to make errors. We can use industrial robots to do this for us.
Drew knows how to weld.
Okay, great. Drew knows everything. Whenever I ask a question, Jacob will say, Drew knows this, Drew knows that. Yeah, okay, good. So they can do welding things, a lot of other things. But however, if you use this industrial robot to machine something for you, suppose, and you can just change the hand to this machining tool, and you want this guy and to machine something for you instead of using the CNC. And what will happen, guys? Let me ask you a question. So my point is, and this guy is very useful for us to help us do something in the harsh, unfriendly environments, right? However, if we want this guy to do some machining work, and we don't want CNN, we don't want to use the CNC. You know CNC, right? Computational numerical control system. We have a CNC machine there. We don't want to use CNC. We want to use these industrial robots to do some machining work for us. And what problem you will see? You will run into that. The problem is that, and so this guy is flexible enough, but it is not rigid enough. Because these guys joints, right? They have weight joint and shoulder joint, elbow joint, maybe have wrist joints, also these finger joints. And if you ask this guy to close the hand to hold this is a machining tool, and the rigid is a problem. It's not rigid enough. If the rigid is not enough, what will happen, guys? So this is my workpiece. But suppose this is my workpiece, okay? This is my workpiece. My hand is the industrial robot hand. And my hand is holding a machine tool. I want to machine this surface. Machine this is about, it's a feeder rate depth card I use 0.5 millimeter, right? Whenever this is my hand with the tool is contacting with this is the workpiece, and what will happen, guys? Based on Newton's third law, what will happen? And your hand, the hand will get this is the reaction force and from this workpiece, okay? Originally, you want to go deeper, 0.5 millimeter. However, you cannot do that. And you can maybe you can just go 0.35 millimeter. Okay? So how to offset and this is inaccuracy? Did that make sense, guys? Originally, so for this one, for very simple maneuver, I want to remove the layer of 0.5 millimeter. However, when my hand is contacting this is workpiece because Newton's law, so actually my hand can only pull down to 0.35 millimeter. 0.35 and 0.5, and they are huge difference, right? That means your machining is not accurate. And how can you just offset, compensate this is the problem? And we use these industrial rollers to help us. Okay, 0.5 is our targeted value. If if we use this target value as our initial value, and we will get 0.35. So this is 0.35 and 0.5 is a huge difference, right? So in order to get our desired target value 0.5, and what should we do? We should go a little bit further. Maybe we should go to 0.75, right? If we go 0.75, because the action and reaction between the workpiece and the tool, and the final this is the position can be 0.5. And how can we calculate this offset? And we use A1N. Okay. So for here, I'll show you guys. So this is our tool. We have velocity. We have this rotating. So this is a polishing tool, right? It's a polishing tool. So I want to remove all these things. This is my final surface. Desired final surface. This is my desired final surface. But there will be some the profile that you need to remove, right, in order to get this desired final surface. So as I said, because Newton's third law, what's the Newton's third law? The depth card, we call this the depth card. The depth card is related to your final your tool position. And how can I use ANN and to predict to take care of this offset? That is technical technology, technical problem. And how can I do that? I use ANN. How I use ANN? If this is my depth card, and my feeder rate, my true depth card will be this. If for my different depth card, for example, from here to here, if I still want to get the desired the surface, and I need to use another depth card. So, artificial intelligence in industrial robots teaching the IR to account for its insufficient stiffness, rigidity. Right? So desired material removed, neural network, and you got offset value of your depth card, and you need to when you put your hand in your position, you must take care of this offset value. Otherwise, the surface will not be the desired one. Okay? Any questions for me? No question. So online guys, do you have any questions? No, okay. So let's move on. Design of neural network. So this is a two neural network, and this guy is only have one layer, one middle layer, hidden layer. We call hidden layer. So this guy has two hidden layer. Okay, this one, this is called one layer, and this this is the second layer, first layer and second layer. So this is one input value, one output value. This is also has one input value and one output value. And you can see clearly for these two hidden layers. So each neuron is connected to all of neurons for the next layer, right? So I want you guys, because we don't have the sensor to sense the true depth of card of materials, so I just give you a mathematical model. Okay, so we want to simulate this machining task. We use this one to mimic a nonlinear function. And we have a nonlinear function, cubic function. This one is used. Represents nonlinear relationship between inputs and outputs. Right? So I want to approximate this nonlinear function. Given one x value, and you will get a y value. Y value is output. Okay, so, when I teach you guys, I want you listen to what I say. If you don't listen to what I say, and you need to use more time to figure out what I just said. Right? Now here are procedures to build the ANN. So as I said, this Wednesday I'm going to walk you guys through on how to use MATLAB to construct and train the ANN. I'm going to show you a little bit.
Wait, at the start of class, you said you were going to show us abacus on it. Did you mean to say math?
Abacus?
Yes.
Did I say abacus?
Yeah.
Did I say abacus? No, we don't know you abacus. MATLAB, I misspoke. Abacus is for the spectral modeling. Spectral modeling. This is for another modeling, right? Abacus. I'm sorry, MATLAB. I'm old. MATLAB, okay? MATLAB for the constructing and training the ANN. Abacus is for the structural analysis. So okay, so we use MATLAB. So I don't know what version of MATLAB you are using. So this here is for the 2017, and for the R 2019A, 19B, and something different. I'm going to show you this Wednesday, guys. Okay, no worries. If you see my program does not work, I want to tell you guys my program worked. Okay, and now when I give you my program, it does not work, and you need to figure it out. For this case, I tested this yesterday. 2017, my program works very well. 2019, it give you some error message, but no worries. Just look at the health, and you just fix it very quickly. Okay, guys, and be positive and not do critical thinking. So for this, I use this 2017 as an example to set up a neural network to find the optimal settings for the training of machining process. In order to simulate the nonlinear relationship between the input and output of machining process, and we use this cubic equation and to mimic for the testing purposes, right? Because we do not have the sensor and to get the real, this is a depth of card. So afterwards, the finite, the function, is used to construct a default function fitting network, and with two hidden layers connected. The first hidden layer contains varying amounts of neurons from 10 to 30 in increments of 5 guys. I want you guys to listen carefully, okay? You need to know what I'm expecting you guys to do. Tomorrow, I just give you one example how to build a model, but the following things you need to take care of it. So the second hidden layer contains a constant 10 hidden neurons. The default transfer function is set to 10 sig function for each of the hidden layer neurons. For this Wednesday, I just show you guys how to build a neural network with the first layer 10 neurons, second layer 10 neurons, right? But your guys need to do, let's say the second layer 10 is constant, don't change it. But you need to take care of the 15, 20, 25, 30 neurons for this first layer, right? But I only give you one example. 10 neurons for the first layer, 10 neurons for second layer. It's very easy, you can just change the number, okay? But you need to do that. And we are going to use the 10 sig function for each of these hidden layer neurons. And using values of x from 0 to 100 in increments of 0.01, a large amount of training data, this is a large amount of training data, is created and are used as inputs for the neural network. The target values are obtained for each input by applying the cubic function with each values of x to receive a corresponding target, right? So this is your target, and this is your x. This is your input file, input data. This is your target. One target, one input file, one target. You use this one to train your data, to train your neural network. So for constant parameters of neural network training, the minimum performance value, learning rate, and gradient are all set to 1e-25. This is very, very small, okay? Very, very small. I want you guys to use this one. This is to facilitate my grading. I want all you guys, all groups, use this one as a criteria, and for this is for your ANN network training. The maximum number of epochs is set to 8,000. So the neural network is then trained using the Leverberg-Marquardt, the propagation method. As I told you guys, on the neural network we have CNN, we have RNN, but we will not take care of them because they are higher level. But because you guys are new users, beginners, I want to teach you guys Leverberg-Marquardt. This is a neural network. Okay? If you are interested, I will finish this. This is a lab, and email me, discuss with me, and I'm going to teach you the CNN and ANN, okay? So the MATLAB workspace is cleared of variables, and the trained neural network is cleared of state data. And change the number of neurons in first hidden layer and repeat the training procedure for each of the 5 different neural network accounts. I give you guys, as I said, I will train first. Give you one example. The following things you need to do. Okay, and you have several team members. You can assign. Okay, maybe Jacob do the 15-10, and we'll do the 20-10, and then Ready do the 25-10, and each one will have your own. So this is and how the team works. Okay, guys? I think you guys will be very comfortable with this, right? So then combine them together, that's a very good level. But you need to hold each other accountable. The training is repeated for 2 additional scenarios. Normalize the data and normalize the data with the single hidden layer. And data was normalized in a range of -1, using the max function within MATLAB. So given one data, one input data, you must normalize it. Why I want you guys to normalize it? Because if you use the normalized input and you result, you can train your finish training your ANN much faster, right? So the procedure used to train the industrial rover. I can finish very quickly, guys. So collecting training data and testing data from the industrial rover And for the manufacturing processes, rubber hand is replaced by a machining tool. So we will not replace it, but we just simply it is replaced. Construct neural network using optimized setting in order to calculate the offset of the trajectory for optimizing the manufacturing processes, and train the neural network in MATLAB and using the training data with the Leverberg propagation method. The test the train neural network and then use the predict value and from the neural network to validate those values against the known testing data. And using this trained neural network to calculate the offset values and for the manufacturing processes once the input data is given. And this can be done through online predicting or offline predicting of the offset values. Apply the offset values to optimize the two parts of the industrial robot. So after you finish training your data, I will give you four true values, and then you use this your trained ANN, and for each of these four values get the target, get this offset value. Okay, guys? So algorithm. So the 10 sig is this is function of 10 sig, and you should know that abacus, I'm sorry, because I use abacus all the time. MATLAB knows this is 10 sig.